Okay, David, do you want to introduce Leonardo?
Okay. All right, thanks a lot. And thank you to the organizers of this wonderful conference. The first talk today will be by Leonardo Rastelli. It's a review talk, carving out the space of effective field theories. Leonardo, take it away.
Thank you very much. It's an honor to give the first talk in this truly global meeting, and thanks to the organizers for their hard work and for putting together this really innovative program. So I've been asked to survey recent progress on constraints on effective field theory by bootstrap methods. The general framework is well known. So effective field theory is a universal tool to organize physics, energy scale by energy scale, and enforce general principles of quantum mechanics and relativity. And so we can be agnostic about what happens at very high energy and focus on the relevant low energy degrees of freedom of whatever physics we want to study. And so we assume that there is a high scale throughout the talk. The UV cutoff of the effective field theory will be denoted by the letter capital M. And we write down the most general Lagrangian compatible with the symmetries. In fact, here and throughout, it will be much more convenient to parameterize the effective field theory in terms of an on-shell process. So here, for simplicity, I'm considering some simple scalar model at tree level, and I'm writing the most general expression of the Mandelstam invariance, which since the theoretic level must be analytic in ST and U. And so we start seeing G2, G3, etc., an infinite tower of so-called Wilson coefficients that parameterize the infinite tower of non-renormalizable higher derivative interactions. And so from this naive viewpoint, it might appear that all we're doing here is just parameterizing our ignorance about the UV, and really we could write down everything that strikes our fancy. In fact, the most general Wilson coefficients would seem to be allowed, but it has actually long been understood, and this has a long history that goes back to pion physics, that this is very much not the case. So if the effective field theory is to arise as the low energy approximation to some healthy UV complete theory, and we will have to be a little more precise about what we mean by healthy, then the Wilson coefficient, this low energy parameter G2, G3, etc., must obey certain inequalities. And this was emphasized in the seminal paper by Adams et al. In 2006. And so the goal of this recent work is to systematize the kind of constraints you can put on these energy coefficients. And here I'm showing a little preview of the kind of results one can get, some precise carving out of theory space where what is in the blue region here is allowed, what is outside is not allowed. So there are some obvious motivations why we may want to do this. Of course, for zero cosmological constant, flat space is an excellent approximation to the real world. So there are many phenomenological applications, for example, in particle physics, you may think of. For negative cosmological constant, there is a big impetus to this program coming from ADS-CFT, more formal type of motivation. And of course, both formally and phenomenologically, it would be wonderful to extend these ideas for positive cosmological constant, but I will have really nothing to say about this today. Another motivation to pursue this program is, at least superficially, it seems that the inclusion of gravity is rather straightforward. You simply add to the mix a massless spin-2 particle. And so you may think that this is perhaps the most conservative approach to quantum gravity. We just see how far we can get from just applying general principles. And perhaps carving out theory space, it will give us a quantitative approach to the swampland. And so one of the famous questions you may want to answer in this context is whether string theory is the unique theory of gravity that makes sense perturbatively. There are many indications that this is the case. And so the general philosophy here is very much in the spirit of the bootstrap. We want to constrain observables, such as the S matrix or a CFT correlator, from general principles such as analyticity, unitarity, etc. So needless to say, these ideas have a venerable history. The idea that causality and analyticity are linked goes back to, really a century ago, Kramers and Koenig dispersion relations. And many of these ideas were pioneered in the 60s and in fact are now being recycled and discovered in the context of formulating an analytic S matrix for the strong interactions. And that program led by the Veneziano Ampi to the birth of string theory. And so you may legitimately wonder why now? Why is it that these ideas have picked up interest recently? And this is not entirely a sociological question. I think there are good scientific reasons for this. One is that there's a more contemporary emphasis on the space of possibilities, on the landscape of theories, rather than trying to nail down the unique optimal solution of the bootstrap axioms. You really want just to explore possibilities. There is the famous success story of the conformal bootstrap that many of you will have heard about, the serendipitous discovery that in the context of the conformal bootstrap, very interesting theories such as the three-dimensional criticalizing model sit at the boundary, in fact, at the kink of the allowed space of parameters. And the SFT has given us new motivations to study this problem. And finally, I would say that kids these days, by which I mean people younger than me, truly are scared of nothing and have modern computational methods that they're applying to these problems. So I will survey some of the recent progress. I apologize, I've tried to give references as accurately as I could to recent progress, but there's no way I can really give credit to all the enormous amount of work that's been done through the decades in this field. And I will focus on weakly coupled effective field theories. I will explain exactly what I mean, both in flat space and in anticipated space, and both with and without gravity. And one of the points I would like to emphasize throughout the talk is that if you're ever going to find an interesting theory at the kink, you really need to be serious about finding sharp bounds for your theory space, and they have to be quantitative and they have to be precise. So to get oriented, I'm going to start discussing a simple model, perhaps the simplest model you can think of, which is that of a light scalar, light whose mass is much lighter than the cutoff big M. And in fact, to make formula the simplest, I will take it to be massless. I'm writing here the 2-to-2 scattering amplitude at 3 levels is the same I had in the opening slide. So there are, of course, here interactions that correspond to the self-coupling of the scale, and then there's this infinite tower of Wilson coefficients. The most general term that is permutational invariant, because of full crossing symmetry, takes this form, and one word of caution. I will be using throughout the talk the letter U to denote momentum transfer. S, as always, Mandelstam S is the center of mass energy, but U will be momentum transfer in our convention, that minus Q squared related in this fashion to the scattering angle, so that forward scattering corresponds to U going to 0. In some of the literature, it's the letter T that plays the role of momentum transfer. In fact, we can make the model a little bit more interesting, or in fact, significantly more interesting, by allowing for dynamical gravity. So here is the graviton propagator given by this blue expression. And if we want to study gravity in this context, we must work in sufficiently high space-time dimension greater than 4. In dimension strictly 4, the amplitude does not, the exclusive amplitude is exactly 0 because of soft graviton divergences. So you have to work in dimension greater than 4. The assumption of weak coupling can be formalized as follows. So we are really looking at a family of S matrices, a family of connected amplitudes. that are depend on some small parameter epsilon, and all couplings of the effective field theory go to zero as epsilon goes to zero, and so so the theory remains weakly coupled all the way up to the cutoff. So the effective field theory is weakly coupled, but this does not mean that the theory will be weakly coupled at arbitrarily high energy. And an excellent example to keep in mind and guide our intuition is weakly coupled string theory, by which I mean we fix the string coupling to be fixed, small. This could be 10 to the minus 10. It's a fixed number we pick from the get-go. And then the cutoff scale is the string scale, is a scale in which the first massive string resonance appears. And of course, we are perfectly justified to treat string theory at 3 levels. It's an excellent approximation of the physics all the way up to the string scale, and in fact, quite a bit beyond it. But of course, eventually, as you crank up the energy, the theory will become strongly coupled, and eventually we encounter the mysteries of quantum gravity at the Planck scale. So the goal, as I have already emphasized, to try to derive sharp bounds. Well, clearly, given their assumption of weak coupling, all the couplings scale with the same small parameter epsilon, it's clear that we will be constrained to work on ratios of coupling. So there is some sort of homogeneity to the problem. We can scale by an overall positive number and nothing will change. And moreover, by dimensional analysis, we can stick the appropriate power of the cutoff to find a dimensionless ratio of this kind. And the standard intuition from Wilsonian effective field theory will then tell us that we would expect these dimensionless ratios to be of order 1, or to say differently, standard effective field theory scaling would tell us that higher derivative interactions are suppressed by inverse powers of the cutoff. And we would like to confirm this intuition quantitatively by putting sharp boundaries on the allowed region of parameter space. Okay, so that having this model as an illustration, I'm now going to state some general principles about the 2-to-2, the properties that we expect from the 2-to-2 connected amplitude. So the first and least controversial is that unitarity will imply that on the physical S channel cut, by the usual I epsilon prescription, we reach the cut from a little above for positive S. We should have a positive partial wave decomposition. In fact, unitarity gives us a constraint on the spectral density rho j of S. For simplicity here, I'm just focusing on the discontinuity of the amplitude, its imaginary part. We get a bound on the coefficient of the partial wave expansion, which is two-sided. It's positive, but also has an upper bound. However, because of our assumption of weak coupling, given that epsilon is smaller than 1, the spectral density, which includes, of course, the coupling of the two external states with some intermediate heavy state, will be very small. And so we will never explore the upper bound of this constraint. We will assume that the amplitude, so if this was an object, this is the complex S-plane at fixed U. I take U to be in the physical region, fix U and negative, fix U small and negative, and we explore the analyticity properties of the amplitude M in the complex S-plane. So the amplitude should be real analytic. It should be fully crossing symmetric. We will hear a lot more about crossing symmetry later today from Sebastian Misera's talk. This is one of the examples where there is a tension between physical intuition and assumptions and what has been rigorously established. Crossing symmetry is not established even in ordinary quantum field theory in the absence of a gap. And clearly we do not have a gap here because we're dealing with massless gravitons. And so this is really not something I can prove. It's an assumption. We will need some notion of ascending analyticity in the first sheet. And so we will need, again, for fixed U, small and negative, we'll need the amplitude to be analytic, at least for sufficiently large modulus of S. And finally, I left this for last because it's the most interesting assumption we will make, or perhaps the least well known. We will assume that along any ray of approach to large S, for fixed U, this is known as the Regi limit. It's the limit of small angle scattering at high energy. But now in the complex S plane, the amplitude should grow slower than S squared. So the M over S squared goes to 0. And the usual slogan is then means that if I divide the amplitude by 2 powers of S, which is means I do 2 subtractions of the amplitude, then I can write a dispersion relation. So the slogan is 2 subtractions always suffice. Okay, so there's a major caveat to everything I'm going to tell you after this, which is these properties are not established. Even in the context of axiomatic quantum field theory, they're not fully established in all cases. And of course, in the context of quantum gravity, we do not even have a framework to establish them at the moment. And so the working hypothesis, and certainly my very strong belief, is that these are actually relatively conservative assumptions that are meant to encode in the S matrix the notion of asymptotic causality and unitarity, even in the presence of dynamical gravity. And again, the connection between causality and analyticity is very well understood. And there's also a connection between causality, unitarity, and the fact that the amplitude should not grow too fast, should grow sub-exponential, should be polynomially bounded in the complex S plane. And if you assume that, then everything else actually follows. So, so let me discuss this last and perhaps least popular or least well-known property, which is the behavior in the Regi limit. So we are going to be writing down dispersion relation with 2 subtractions. So we really need that the Regi behavior be a little bit better than just S squared. If you recall from the previous slide, the graviton propagator really grows like S squared is the graviton propagator. And so Einstein gravity, or in fact, any Einstein gravity slightly violates this assumption. And the idea is that at the non-perturbative level, the behavior will be a little bit better. This already is cured at the level of 3-level string theory by an infinite tower of massive higher spin that famously, the linear Regi trajectory of the graviton resums itself to a behavior which is softer for large S than S squared. Remember that U is negative. And our hunch is that this is actually a safe assumption, at least for sufficiently high space-time dimension. And the physical picture goes back to this classic work of Amati, Ciafaloni, and Veneziano in the 80s, and is a picture of what happens in gravity, even in quantum gravity, at arbitrarily high energy, but even larger impact parameter. So no matter how, if you fix the energy, no matter how large the energy is, it could be trans-Planckian. If you take the impact parameter, which we can think of it as we can prepare 2-wave packets that are a transverse separation of B, and then classically the impact parameter will be related to the spin and to the energy in this fashion. For large impact parameter, gravity is weakly coupled. And the quantum mechanically, this ratio of 2J over E will be the region of the high energy states on which the intermediate states are mostly peaked. So you can assume that the impact parameter, even quantum mechanically, is given by 2J over E with good approximation for large energy. And perhaps this will be discussed later on in the session on high energy scattering in string theory. But in the crudest form, the argument is then the following. So unitarity tells us that each partial wave is bounded, and the sum will shut off a large J, because a large J we have large impact parameter, and that's when gravity becomes weak. Of course, this argument is really very crude, and one can and should be more precise. This is work in progress to appear by Herring and Zhiboyedov. One can perform a better estimate. First, start in the physical region, large energy on the real axis, and using relatively conservative assumption in the impact parameter representation of the amplitude and carefully estimate the Fourier transform back to, this should be really an U in our conventions, to momentum transfer space, one finds that in dimension greater than 7, the Regi growth assumption is correct. And if you're willing to make somewhat more adventurous, but still rather reasonable assumption, what happens at somewhat smaller region of impact parameter, then this is true in D greater than 5. And once you have this on the real axis, you can extend it in the full upper half complex plane. If you assume, as I would advise you to do, that the amplitude is polynomially bounded there, which is, again, an assumption meant to encode the notion of causality. Okay, so perhaps I've said too much, but I emphasize this point because it's a crucial assumption that we will be making throughout. And let me say something perhaps a little bit more informal. In this string theory community, you're kind of not expected, but there's a sense that quantum gravity is not this terribly exotic thing. More or less, quantum gravity follows the usual rules of quantum, or the usual rules of the games, very much, including quantum mechanics. And so this is, even in the context of quantum gravity, these are not terribly adventurous assumptions. But of course, if you believe that quantum gravity is not in this framework, then I have very little to tell you. So the complex S plane is wonderful because it lets us connect the IR expansion of the amplitude, the one that we want to put bounds on, with the UV. And so the idea is that we're going to write a suitably subtracted dispersion relation for the amplitude. So this is the contour at infinity. So if we divide by 2 power, and then we can use Cauchy theorem. And so this whole contour here, of course, vanishes because we're assuming that the amplitude is analytic here in the middle. And by our behavior on the large arc, we can drop the large arc. That's the Regi assumption. And so we get then a relation between this arc surrounding the low energy region and the cuts, the S and T channel cuts, where we have the positive partial wave decomposition. So the philosophy here is that we want to relate low energy, this is the red arc here, with high energy. We don't know anything about the high energy, except that it's positive. It's a sum over a positive spectral density. And so by this kind of trick, we get to express the low energy parameter as some sort of weighted sums with positive measure of the high energy states. And so there's a long history to this. I'm putting here some of the references. Apologies if I mixed some. This program was started by Adams et al. In 2006, who noticed some simple constraints such as positivity of the leading higher derivative couplings. And it has been made systematic for 2-to-2 scattering in a series of recent papers that use slightly different language and formalism, but essentially telling the same story. So for simplicity, so here in the picture, there was a red cut that was meant to indicate the fact that, of course, we should be including effective field theory loops, as we always do in effective field theory. But remember, we have this parameter epsilon, which is very small. The effective field theory truly is weakly coupled all the way up to the cutoff. And so to leading order, we're perfectly justified in the theory at 3 level, and we'll worry about systematically doing loop corrections later. So we only have poles at low energy in the approximation I'm going to make in the next few slides. And so again, there are several equivalent formalisms. I'm following here the notations and setup of Caron-Yot and Van Duong. So again, we write a dispersion integral of this kind. The reason we divide by S prime times S prime per U is because we want to preserve ST crossing symmetry. And then this is 0. And by deforming the contour, we get to express the low energy parameters in terms of the high energy spectral density. So this is low energy piece, the arc that I had earlier, and this is the high energy piece integration on the cut. And so let's stare at these formulas for a second. So U here is a parameter that has to lie in the, for validity of this approximation to work, has to lie in the physical region between minus m squared, which is the cutoff, and 0. G2, G3, etc. are the low energy Wilson coefficients. And so this is an infinite set of sum rules for each even integer k, each of which is in itself an infinite set of rules because the parameter U is in both sides, expressed in the low energy parameter in terms of the UV data. F2, F4, X6, etc. are perfectly computable and well understood functions that I'm not writing here not to overcrowd the slides. And so that is the essence of this game. And we are agnostic about the UV physics, except that these densities are positives. K here is the number of subtractions, and it follows that only EFT interactions that grow as at least as fast as OS to the K appear on the left-hand side. So for example, you see that the graviton only contributes to the spin to sum rule and then drops out, etc. Now, it's actually the case that one can express the same low energy parameter in multiple different ways in terms of high energy data. So the high energy data on their own obey some non-obvious so-called null constraints. This is an example of one of them. And the origin is in the fact that we have chosen to break the symmetry between S and U by doing a dispersion relation of fixed U and doing the contour integral over S. But of course, the symmetry truly is there. And it's not so surprising that the spectral density, which really encodes light heavy data, would know about low energy crossing symmetry. And so we see from here, just the little scaling argument, that the interesting physics, the interesting dependence on rho, happens at a scale of the order B, B being the impact parameter assigned big M. Okay, so the conclusion and upshot of this analysis is that now we can take the sum rules. For the moment, let me avoid to talk about gravity because the graviton propagator, as you will recall, was singular for U going to 0 in the forward limit. And just expand this in a Taylor expansion. So that gives us an infinite set of constraints for this coupling in terms of positive objects. And this is the kind of program that you can very much put on a computer using semi-definite methods. And you find then a sharp exclusion region of this kind, where, as promised, the dimensionless couplings obey two-sided bound. It's a compact region. And this is a very nice conclusion because it means that power counting follows from causality. That is the takeaway slogan. There is a beautiful geometric picture for all of this that comes from viewing the problem from a slightly different perspective. So we can also, of course, express each of the individual couplings in the notation of these gentlemen, Arkani, Hamed, Wang, and Wang. They parameterize the coupling in terms of an expansion in S and U, which of course they would call T, but I'm trying to uniformize it to the notations of this talk. And the couplings are expressed again as weighted positive sums. These PIs are positive that depend on the spectral, on the mass and spin of the heavy states with some known functions X of L, K, and Q. And so the geometry is interesting and complicated, but there's a nice trick that was explained in the second paper, that by general linear transformation, one can re-express the couplings in a much simpler form that makes it clear that the right-hand side is just the product of two moment curves, one for the masses and the other for the spin. And so we can then apply known mathematical descriptions of this convex hull, at least in the limit, in the infinite dimension limit where we keep all the Wilson coefficients. And so this is a sketch of how the geometry looks like. There's a convex hull whose boundaries can be characterized mathematically in terms of these polytopes. And then crossing symmetry is imposed after by slicing this unitary hull with a symmetry plane, and the crossing and the null relation would then arise from the intersection. And okay, it's pleasing to see that in the limit of infinitely many derivatives, this method agrees with the semi-definite method. Earlier, there is a little bit of an error due to the truncation to finite number of couplings. The graviton pole presents a difficulty. It is singular in the forward limit, and you really cannot subtract it because it grows like S squared. And so if you subtract it, you violate the Regi growth assumption. But there is a measure of resolution, which is who told you had to expand in the forward limit in the first place? We can win by eliminating the dots on the left-hand side by taking linear combination of this infinite set of some rule and finding a left-hand side that depends only on a finite number of low-energy coupling in terms of a slightly more complicated right-hand side. And then we milk this relation by convolving with a suitable function, which in impact parameter space takes the form of a step function. So this is just, the computer will give you that. You optimize the bounds to find the best constraints, and that's what you find. And so the physical picture, rather than measuring couplings in the forward limit, which is dangerous because of the graviton pole, we measure them at small impact parameter, b of the order of 1/m, where m is the UV cutoff. And so this is the same kinematics that this beautiful thought experiment of Camaño, Edelson, Madsen, and Zhiboyedov, that unfortunately I don't have time to review here, but I invite you to learn about it. But now in the framework of the asymmetrics booster where we can put sharp bounds. And so this is, I'm flashing some of the bounds. So one upshot of this in different dimensions is that the coupling G2 that in the paper of Adams et al. Was the one that was strictly positive now is allowed to be a little bit negative because gravity provide a time delay that can compensate for it. So all of this was in the context of a model with external scalars. We would like to do gravitons. That's a little bit more involved. There is some work on external spin, but as always, supersymmetry provides a shortcut. In particular, maximal supersymmetry allows us to study scattering of supergravitons in terms of an auxiliary scalar amplitude. And the scalar amplitude actually has improved Regi behavior of this sort. And so it starts as 1/STU. And the leading correction is a constant, which is related to the famous R⁴ corrections to Eisen-Hilbert. And we can now put a rigorous upper bound on it, a weak coupling. Again, we're assuming that the Newton constant is small at the unit of the cutoff. And this is the coupling, the bound that we find in 10 dimensions. So the very interesting conclusion here is that if gravitons couple to some very heavy state, and we integrate out the state to get to R⁴ correction, well, that coupling cannot be arbitrarily high. That interaction must shut off as the Newton constant goes to 0 because of this upper bound. Let me mention that there's also a lower bound, which in our limit of small coupling would go to 0. It's a bound when the coupling is expressed in Planck units. By Guerrero, Prendos, and Vera, and perhaps this will be discussed this is just an excuse for me to advertise the session later today that will study other aspects of the asymmetrics booster, including strong coupling. A cute application of this framework is that these sum rules that were derived in a slightly different but complete equivalent formalism by Tolle, Wang, and Zhu allow you to rule out amplitude very soft behavior, such as weakly growing Galileons. The exact massless graviton was already, Galileon was already ruled out in the original Adams et al. Papers, but now you can do more, even with a small mass. So now this, if you remember this picture of the 3D Ising model sitting at a kink, you may now wonder, where do actual theories sit in this space that we have carved out? And the interesting conclusion that was first noticed in the EFT paper and then explored more systematically by Bernd Kosmopoulou and Zhiboyedov is that physical theories actually do seem to lie kind of at the edge of the exclusion region. Here is actually, I'm not sure if you can even see it. There is a sequence of theories here that are this black segment. And there is a nice principle that one can experimentally notice, namely, if one looks at what contributes to this amplitude, one sees that there is a suppression of states of high spin as intermediate states. And so if you take that as a principle and impose by hand that high spin states are suppressed in this particular plot by something of the order 10 to the minus 2, that carves out, this is a zooming in of this plot, that carves out a small region given by these jagged lines, which actually focuses in on the physical amplitude. That's a very interesting observation. It is not, none of this is visible at the level of 2-2 scattering, because at the level of 2-2 scattering, the rigorous constraints we have imposed will allow for this whole region. But of course, this is just necessary conditions. And so the idea is that perhaps in the fullness of time, end-to-end scattering or some other consistency principle will give us a much smaller region of parameter space.
Leonardo, you have about 4 minutes.
Really? Okay, so now let me now move on to ADS. I'll be quick. First, because I only 4 minutes, although can I go on? Can I go a couple of minutes up over? But thankfully, my talk will be followed by Simone Carognot's talk, who will have a significant overlap on this last part of my talk. So now I want to describe how the story works in asymptotically ADS space. Many of the words that I can say are the same. So we want to study effective field theories that are weakly coupled in anti-de Sitter space. And in the purest model, we take the graviton to be the only state below some high mass scale M. And so, of course, to leading order, we just have Einstein-Hilbert with a cosmological constant that Weinberg taught us. And then we systematically correct it with higher curvature term, which schematically take this form. And the assumption of weak coupling is that we really have a hierarchy of scale, again, between the cutoff scale, which is much larger than the ADS scale, and the Planck scale, which is much, much larger than the cutoff scale. And power counting would tell us that the coupling should be suppressed by powers of the intermediate UV cutoff state. For example, in string theory, these couplings come with powers of alpha prime. So that's a string scale, not the Planck scale. And again, this thought experiment by Kamani et al. Confirmed this, but only parametrically. If the couplings do not scale parametrically with the expected inverse powers of 1 over m, you find a violation of asymptotic causality in the form of a time advance. And we would like to do better, like to derive these bounds rigorously. And the idea is that, of course, the SFT is the way to do it, because the theory is non-perturbatively defined by the boundary CFT. And so we're looking at the special corner of the conformal bootstrap for large NCFT with a large gap, delta gap. However, standard bootstrap methods, such as the numerical oracle, are inadequate because of the large contribution from single trace composites, since we are a large N, remember. And the right tool are dispersive sum rules. So for simplicity, I will again focus on a model where we're introducing an additional light scalar in the mix and probe the question by looking at the corresponding dual CFT correlator of 4 primary scalar operators. This is a slide that I would like you to pay some attention to, especially if you're not part of this community. It's something that, it's a tool that has become very useful in the conformal bootstrap with an analytic flavor. And it's a notion of double commutator, of double discontinuity. It's the correct analog of taking the imaginary part of the amplitude m in flat space, or taking its discontinuity throughout the cut. The analog in CFT is the double commutator, illustrated here in this famous Lorentzian kinematic region. So we take the double commutator. So clearly this only makes sense in Lorentzian signature. And these are time-like separated 1, 2, and 3, 4 interline separated points. And the same Lorentzian kinematic that appears in the proof of the bound on chaos and in the Regi limit, which correspond to boosting 1 and 3 laterally to one another. And so much like the full amplitude after doing a subtraction is reconstructed from its discontinuity, the full correlator is reconstructed from the double discontinuity along two different channels. And the property that will be essential for our application is that the disk annihilates intermediate double traces. This is completely analogous to what happens in flat space, where the imaginary part vanishes, essentially because it reexpresses the amplitude in terms of the lower amplitude, lower loop level.
Leonardo, so, please try to wrap up pretty soon.
Yes, I need a couple of minutes to get to the punchline, but so there is a bewildering array of formalism in which one can discuss these dispersion relations. I'm flashing here some names, but the main message can be explained with a rather physical picture. So we express causality as the vanishing of a commutator for x1 and x3 space-like, as indicated in the picture here. And to get the strongest bound, we integrate x1 and x3 along space-like separated null rays. So 1 and 3 are at these 2 points in this two-dimensional null plane, but they're separated in the transverse space-like direction. And so by convolving this commutator with a kernel, we get an equality of this kind. And the main takeaway is that essentially this gives the double commutator or double discontinuity. In the absence of the kernel, we could simply replace each of these products, of these Weidmann products, with double commutators, right? So, because null integrated operators annihilate the vacuum. This is a little bit too fast because the kernel has poles. And so what you really get is a sum rule that morally annihilates double traces except for a finite number of Regi trajectories. So one finds a sum rule when expanding the correlator in the S-channel conformal block decomposition that gets contribution that has double zeros on all double traces whose twist is greater than some minimal twist. So perhaps the linear Redi trajectory, for example, will not be like that. You will only have single zeros there. And so we now apply this to our model. By assumption, the 555 correlator gets contribution from the only single trace that contribute for twist below the gap is the stress tensor and the identity. Then, of course, you have double traces. You have additional composites such as quadruple traces or composites of phi and t. And then, of course, above the gap, anything goes. The only thing that we assume here is unitarity. And so given a dispersive function, we can split its action on the light and heavy state and find this sort of tautological relation. But the crucial point here is that the action of the function of the light states is of order 1 over n squared, because the double traces exactly n equals infinity drop out. And so you only get the contribution from the order 1 over n squared correction to the anomalous dimensional double trace and OP coefficient, as well as from the order 1 over n squared graviton exchange. And so this is precisely the part that can be computed from the low energy effective field theory, parameterized in terms of Wilson coefficients. And so we are done. If we find a non-negative omega when acting on heavy state, we have found a constraint that just captures the single trace data and higher derivative correction to the quartic coupling at low energy. And this is completely analogous to the flat space sum rule. So I trust that Simon will explain this better in this talk, but let me just give you the punchline. By this kind of methods, we're able to construct a family of sum rules that achieve bulk focusing. And so we can repeat in ADS the trick that we had in flat space of measuring couplings as small ADS impact parameter. And by doing so, we can uplift to ADS the rigorous flat space bound that we had earlier and achieve this proof of bulk locality with a sharp bound. And so one of the great promises of the subject is to make the transition from ADS to flat space more precise. And the CFT bootstrap is completely rigorous. The axioms are clear. They've recently been proved by Richkov and Kravchuk in the context, starting from the Euclidean axioms at the level of 2-to-2 correlators. The Regi bound is not an issue. There's a non-perturbative Regi bound with Regi intercept 1. And so if we could make this transition more precise, we would actually have justified the S-matrix bootstrap axioms. Of course, this is still a tall order, but making sense of it is one of the great open problems in the subject. And so let me summarize. This is the beginning of a program, both in flat space and ADS, to constrain weakly coupled effective field theory with sharp bounds. And the take-home message is causality is truly powerful. And there's a large list of things to do. Some of them rather straightforward, such as value generalization, more correlators, more external spin loops, etc. And some of that deep, such as whether we can answer deep questions, such as the existence of pure gravity. Thank you very much.
Okay, let's all thank Leonardo. We have about 5 minutes for questions. So there's a question from...
Sorry, I want to acknowledge my amazing collaborator for teaching me everything that I know about this subject, and also Sasha Zhiboyev.
There's a question from Alejandra. Go ahead.
Hi, Leonardo. I have a very quick question. I was wondering if this program would say anything on a bound on the number of space-time dimensions.
Not that I know of.
Do you expect it to be an outcome in the long term, or?
One can always hope, but at this stage, not really. I mean, these axioms for 2-to-2 scattering, I believe, would work in any dimension. Perhaps in very high dimension, you can mix this with the simplification of gravity in large dimensions, but I really haven't thought about it.
Okay, thank you.
Okay, Daniel.
Hi, Leonardo. Thanks for the nice talk. I'm a bit puzzled about the role of the weak coupling assumption in this. For example, I mean, you could try to do the whole story also for weakly interacting quarks and gluons, but you would totally miss what actually happened in the infrared of the theory because
you couldn't do that for.
Okay, good. So why can't I do that?
Well, because I'm looking at asymptotic states.
But is that I guess, yeah, okay, so that's an assumption somehow. I mean, yeah, I guess that's the thing. You're kind of perturbative, but then not perturbative. And I guess I'm having trouble figuring that out.
Let me emphasize this again. What is perturbative is the effective field theory description. The full theory really need not be perturbative. And it will not be perturbative sufficiently high energy. But I am assuming that I have a description of the asymptotic states. So it's important that I'm looking at physical asymptotic states. And there's a description of the physical asymptotic states in terms of some degrees of freedom that are weakly coupled all the way up to the UV cutoff. The UV cutoff, of course, is a sliding cutoff, as always.
Yeah, but for example, you have massless particles, right? So you're ignoring, I mean, you're talking about an S matrix that doesn't exist. And I thought the excuse for that was that it's weak coupling, so you're ignoring the infrared divergences and so on, right?
No. The infrared divergences are absent in sufficiently high dimensions. So yes, in 4 dimensions, one needs to be much more careful. And I was thinking of adding a slide about it, but then in the interest of time, I didn't. In 4 dimensions, of course, you will find an infrared divergence, and that will actually be very nicely regulated by ADS4. So I would be actually hopeful that one can, either using ADS4 or using some sort of other more inclusive kind of infrared safe amplitude, one could try to extend the discussion, the flat space discussion, to 4 dimensions. But in dimension greater than 4, there's no issue with infrared divergences.
Yeah, thanks.
Okay, we have time for one more from Sergey.
Hi, Leonardo. Yeah, it's also about weak coupling assumption. So some of the bounds don't require it, like the initial bound on d5 to the 4 coefficient. Are there more quantities like that which don't require weak coupling assumption and can be constrained?
Sorry. The weak coupling assumption entered most centrally in the treatment of the effect of in the fact that I treated the effective field theory at 3 level.
Right.
This argument of expressing, if you are willing to just integrate, so if you go back to this picture, if you're willing to declare that the integral over this arc in the infrared region is my physical quantity, then there's no need to make any weak coupling assumption. The weak coupling assumption comes if I want to relate that arc to the standard Wilson coefficient, and then I do some matching of this on-shell quantity to the Wilson coefficient at 3 level, or systematic corrected loop by loop. But, well, again, no, at the full non-perturbative level, it's true under our axiom, which of course is a good question, but under our axiom, it's true that I can express this arc in terms of an integral with a positive density over the cuts.
Okay, thanks a lot. We have a shortened question period. So let's all thank Leonardo again and get ready for the next speaker.